Welcome to Lecture 18 of Electrical Engineering 525. In this lecture, we're going to be studying some material from Section 3 of Chapter 8 dealing with Endfire and ordinary Endfire arrays. And in this discussion, we'll learn the distinction between those two different kinds of arrays. So let's go ahead and jump right into this. The first problem will be a modified version of problem 8.3-5E. And what I want to challenge you to do here in this problem is to sketch the array factor for an array of 5 equally spaced elements with uniform current amplitudes, and D is equal to lambda over 2. Theta naught is 180 degrees, which is the Endfire case. Now remember that actually 0 degrees is also what we call the Endfire case, and 90 degrees is the broadside case. So we're looking at an Endfire case here. We want the main beam to be in the negative Z direction, or 180 degrees, and the spacing between the elements is 1/2 wavelength. So let's see how we would tackle this problem. Well, first of all, we can start by noting that, as was the case in a previous problem that we discussed, 8.3-7, since n is again equal to 5 in this problem, then f of c, the normalized pattern factor, is equal to sine of 5 times c over 2 divided by 5 sine of c over 2. Now, d in this case, as we said here, d is equal to 1/2 wavelength, and therefore beta d is equal to 2 pi over lambda times lambda over 2, or just pi. Now, alpha, once we have beta d, then we can easily find alpha, because alpha is equal to minus beta d cosine theta naught, and so that's minus pi times the cosine of 180 degrees, or positive pi. So again, now we have alpha is equal to pi, and beta d is equal to pi. And remember that we want to plot f of c from alpha minus beta d to alpha plus beta d. So since alpha and beta d are both equal to pi, then alpha minus beta d is 0, and alpha plus beta d is 2 pi. So we will want, in this problem, to plot f of c, actually the magnitude of f of c. We want to plot that from c equals 0 to c equals 2 pi. And so when we do that, this is the graph that we get. And once again, now, just to make sure this is perfectly clear, this plot right here is a plot of the magnitude of f of c as a function of c, where f of c is this function right here, which we have already seen before. Using L'Hopital's rule, we find out that the function goes to 1 at c equals 0 and at c equals 2 pi. We can also easily find out that at 2 pi over 5 and 4 pi over 5, 6 pi over 5, and 8 pi over 5, it goes to 0. And then we have these lobes in between the main lobe and the grading lobe. So now, as usual, to get the polar plot, what we'll do is we'll extend this line from 0, and then from there we go over alpha to find the center of the pattern. Remember, alpha is equal to pi, so we go over here, and this gives us the center. and then we're calling that beta d is equal to pi, then we have the plot will be from alpha minus beta d to alpha plus beta d. So we can drop the vertical line here at 2 pi, and we see that the circle will go from 0 to 2 pi. We can go ahead and draw in this top part of the circle, and then it's also useful to drop vertical lines from the zeros of the plot above, because this will help us to keep track of where we have zeros in our polar plot. So we drop vertical lines from these zeros, and we find out where those vertical lines hit the circle, and then we draw radial lines from the origin of the circle out to those places, and that helps us to define where these lobes are. And then of course for each one of these lobes we go out as far as is indicated by the lobe above and the f of c plot. So the two lobes at 0 and 2 pi will go all the way and meet the circle at a magnitude of 1, but the others will not go that far. And this is the plot that we will get for this problem. And notice that it does indeed have a main beam in the 180 degree direction, or the negative z direction, but it also has a main beam, or I mean some would call it a grading lobe, but the point is that this has the same magnitude as the main beam, this additional beam here in the 0 degree direction. And then we also have these side lobes here. So that's the result for this case, where once again we have an Endfire case, and d is equal to lambda over 2. Now in the next problem we want to start thinking about an ordinary Endfire array, and an ordinary Endfire array is one in which there's only one, it still has one beam pointing off in either the 0 degree direction or the 180 degree direction, but the spacing is chosen in such a way that we only have one main beam rather than two main beams, as is the case here. So let's see how this will go. So to pursue this question further, we're going to look at problem 8.3-8, and this problem asks us to design and plot the array factor for an ordinary Endfire 5-element uniformly excited linear array with spacings d equals 0.35 lambda. And it says use theta naught equals 180 degrees, just as we did in the previous problem. So once again we have 5 elements. Once again the current on each element has the same magnitude. Once again we're aiming for the main beam to be in the direction of 180 degrees, but the only difference really is that in this, whereas in the previous case the distance, the spacing between elements was 1/2 lambda, now the spacing is 0.35 lambda. And so we're asked to find alpha, but we're also challenged to design and plot the array factor. Now let's explore this idea, ordinary Endfire. What does it mean? Well, there are two conditions for an array to be designated as ordinary Endfire. The first condition is just the Endfire condition. This is true for any Endfire array, that theta naught must be equal 0 degrees or 180 degrees. As we said above, 90 degrees would be broadside direction, and either 0 degrees or 180 degrees would be the Endfire direction. So that's one condition, and that's the Endfire condition. But then what gives us an ordinary Endfire array is this additional condition here. And if you wish, you could interpret this d as being less than or equal to rather than just less than. In fact, when you do the test 18, go ahead and interpret this condition as being less than or equal to. And but the condition is that the spacing between the elements should be less than or equal to 1/2 lambda multiplied by the quantity 1 minus 1 over 2n, where n is the number of elements in the array. And what we will see, both from this problem and from the test problem, is that by decreasing the distance, the separation like this, in this manner, we make sure that there's only one main beam rather than two, as was the case up here in this problem. So, now to check and make sure that the present problem really is ordinary Endfire, recall that we were told in this problem to use theta naught equals 180 degrees, so that immediately satisfies, or immediately means that condition 1 is satisfied. And now what about condition 2? Well, remember that we're told that d is equal to 0.35 lambda. So let's check and see if that d satisfies condition 2. Well, if we recall that in this case we have n equals 5 element, it's a 5-element array, then condition 2 becomes d is less than, and again it could be less than or equal to, that's fine, less than or equal to lambda over 2 times 1 minus 1 over 2 times 5. So this is lambda over 2 times 1 minus 1/10, which is lambda over 2 times 9/10, which is 9 lambda over 20, or 0.45 lambda. So 0.45 lambda in this case would be the largest possible d that would still satisfy the Endfire condition. The ordinary Endfire condition. But the d that we're given here is 0.35 lambda, which is even smaller than that. So certainly if 0.45 lambda is small enough to satisfy the ordinary Endfire condition here, then definitely 0.35 lambda also satisfies it. So both conditions, both ordinary Endfire conditions are satisfied, and therefore we can go ahead and proceed with this problem. Now alpha, we're asked to find alpha and also the plot. Alpha is very simple, again, as has been the case repeatedly, as we've seen repeatedly. Alpha is minus beta d cosine theta naught, so that's minus 2 pi over lambda times 0.35 lambda times the cosine of 180 degrees, and that gives us simply 0.7 pi. So alpha is 0.7 pi. Similarly, beta d is 2 pi over lambda times 0.35 lambda, and so that is also 0.7 pi. And so now if the plot, since the plot will go from alpha minus beta d to alpha plus beta d, and since alpha and beta d are both equal to 0.7 pi, then we have alpha minus beta d is 0, and alpha plus beta d is 1.4 pi. So using the same plot for the magnitude of f of c that we had in the previous problem, we see that the only difference here is that instead of plotting our polar plot here from 0 to 2 pi, we're only going to occupy the region down here from 0 to 7 pi over 5, or 1.4 pi. Now, just to make sure it's clear how I got that, let's drop the vertical line from 0, and then as usual we'll go move over from that the distance alpha, and alpha in this case is 0.7 pi. So if we go 0.7 pi, then in the positive direction this time, we get to here, and that's the center of our circle. And then since beta d is equal to 0.7 pi, we go alpha minus beta d is 0, alpha plus beta d is 1.4 pi. So our circle is going to be from 0 to 1.4 pi, and then we can go ahead and draw in this upper circle. Once we have done that, then we can draw vertical lines from the zeros again, as we did in the previous problem, and that helps us to, once we draw radial lines to the points where those vertical lines touch the circle, we can identify the angles in the polar plot where we will have nulls, and we are also able then to fill in between those radial lines. We're ready to fill in the lobes with the correct magnitudes. This first lobe over here goes all the way out to 1, since the magnitude here is 1. This one is somewhat smaller than 1, and this is smaller still, and then this lobe would have the same magnitude. Now notice that we're coming here to the midpoint of this lobe, which is the maximum. So that's why this lobe right here has the same distance from the origin as this lobe, which corresponds to this part of the f of c curve. But again, it's important to note that this does not reach all the way out to 1. So we see that we have only one main beam in this case in the 180 degree direction, rather than two main beams as we did here in this case. So that's why this is an Endfire case, but the problem we considered here satisfies the ordinary Endfire condition, which gives us just one main beam. And that is summarized there in those few words. And that finishes this lecture as well, because now you will be ready to do test 18, which asks you to do one of the problems in the book, and it asks you to choose the maximum D to satisfy the ordinary Endfire conditions, and then it asks you what alpha and D will be for that array, and finally it asks you what the magnitude of the pattern will be in the opposite of the desired Endfire direction. So you'll see all of those details once you get to the test. But that concludes the video for lecture 18, and so good luck.